When talking about atoms, we can talk about X-rays. X-rays are, again, high energy light, almost as high as gamma ray emission, between ultraviolet and gamma rays. X-rays are highly penetrating, very ionizing forms of radiation. Now, X-rays are incredibly useful when probing the inner structure of atoms, molecules, because if you want to measure the size of something, you have to use a wavelength of light that is around the same size as the object you're measuring. If the wavelength's too long, it can't see the object, if you will. You've probably experienced this if you've ever been in the ocean, right? If you're standing in the ocean and a big wave comes by, that wave doesn't even know you exist, right? It passes right by you. You don't really create any ripples downstream from an ocean. But in a still pond, if you drop a rock and you see the ripples come off, you are an obstruction to those short wavelength waves. Another wonderful example is radio waves. You can be in a building and radio waves can pass right through the building to your cell phone or to your AM or FM radio, ignoring the fact that there's a wall between you and the transmitter. So X-rays are high energy, high frequency, small wavelength light that can be used to probe the nature of atoms and molecules. Crystals especially for X-ray use. And of course, you've probably heard of X-rays from a medical standpoint, having an X-ray done or having a CT scan done. And we'll talk about the medical uses of X-rays at the end of this lecture. So if you set up a cathode ray tube, a CRT, which is basically a high energy, a high voltage tube where electrons are stripped off of a material and accelerated through a high voltage to smash into an anode. So the X-ray emission from the anode when these electrons crash into it of a cathode ray tube looks like this. So the intensity of the X-rays increases with increasing frequency up to a point, and then there's a cutoff frequency where you don't get X-rays beyond that point. But note that, as your book points out, there are 2 bumps or 3 bumps in this spectrum. So the smooth black curve is a continuous spectrum of what's called Bremsstrahlung radiation. Bremsstrahlung means breaking. So when the X-rays crash into they stop, they decelerate. As they crash into the anode material, they can give off X-rays. But also there are these 2 peaks that are called characteristic X-rays. These, in this case, it's the K alpha line and the K beta line. These characteristic X-rays give us some insight as to what's going on inside the atoms of the material that makes up the anode. Now again, the maximum energy of these electrons that smash into the anode depends upon the charge on an electron and the voltage that the electron is being accelerated across. That is equal to the energy of the photon, the X-ray that's given off, which is Planck's constant times the frequency. And in this case, the maximum energy gives you the maximum frequency. So if you want to increase the maximum frequency, you have to increase the potential across the cathode ray tube, give a bigger voltage, which causes the electrons to smash more energetically into the anode. Now, electrons that strike the anode material can kick off electrons in an atom. So if we have a positively charged nucleus, and we have electrons in their orbits around an atom, get a simple solar system model of the electron. So imagine there's 6 protons. I won't draw them all in detail. This atom happens to have 6 electrons. And another electron can come in at high speed, smash and hit one of these other electrons, interact with it, and kick the electron out. Or in this case, kick this electron out. That leaves an opening in the atom where an electron can fall in. Now, occasionally, this electron will come in and smash into one of the inner shell electrons, kicking that electron out, leaving a gap. This electron also, because it has such high energy, doesn't stay either. It flies off after it crashes and then disappears. This opening, atom doesn't like it, right? All of these electrons now can see that there's a missing electron down here, and one of them will likely jump down into that inner shell and give off an X-ray photon. How energetic that X-ray is depends on how big of a jump it falls. Maybe the electron jumps from a higher orbit, giving you a bigger jump, giving you a more energetic X-ray. How big an X-ray that comes off of this jump depends on the energy transition between these two states. That energy transition between the two states is material specific. So we can use X-rays in this setup to probe the inner workings of atoms. So we're going to talk about that next, talking about how you can use X-rays, or this cathode ray tube, electrons smashing into atoms. You can study the frequency of the X-rays given off, and it actually lets you know what element you're playing with. So when an accelerated electron in the CRT comes in, it can knock an electron out of any possible orbit. And we'll talk more about orbitals later in this chapter. But some electrons are actually close to the nucleus and are very tightly bound. Other electrons are further away from the nucleus, and again, remembering how electrostatic forces work, the further two charges are away from one another, the weaker the pull. Additionally, if you're an electron out here in this fourth orbit, the positive nucleus is shielded by all of the other electrons around it. So you not only are further away from that positively charged nucleus, you also see it through a cloud of negative charge, which means you're less strongly attracted to it. When an electron comes in and kicks out an electron, let's say from the first inner orbit, an electron can fall in from 2 to 1, or from 3 to 1, or from 4 to 1. Or the electron could come in and knock an electron out of 2. And so then you see the electron can fall from 3 to 2 or 4 to 2. Each of these transitions, from 2 to 1, or from 3 to 1, or from 3 to 2, or from 4 to 2, and so on, each of these transitions is given a letter and a Greek alphabet designation. So the most common inner shell electron transition from 2 to 1 is called K alpha, and that's the bigger peak if you look at that Bremsstrahlung plot in the book and the one I had up on the board earlier in this video. That is the larger frequency. K sub B is a bigger transition, so it's a smaller bump. It happens a little less often, but it is a bigger energy jump, so it's a higher frequency. 3 to 2 is actually a lower transition. 4 to 2 is again slightly more energetic than 3 to 2. That's called an L alpha and an L beta transition. So K alpha is really what we want to focus on. We want to find the K alpha line, and then you can use different materials and see what frequencies come about. And what happens is you get what's called the Mosley plot, and there's a link to it here to my right. The Mosley plot is just a plot of the frequency of the K alpha photon, the X-ray photon, as a function of the number of protons in the nucleus, or the positive charge in the nucleus of the atom. And it's a wonderful, beautiful linear plot that relates, in fact, it's the square root of the frequency, to the number of protons in the nucleus. So if you have an element and you're unsure of where it goes on the periodic table, the periodic table was initially developed by keeping columns of elements that had similar properties. Like, for example, all the noble gases on the right-hand side, alkalides, all of these different, materials that have similar properties. Carbon can bond 4 times, so can silicon, and so on. These similar columns were materials of similar properties. But how do you know it's right? How do you know that the periodic table that oxygen comes after nitrogen or that nitrogen comes after carbon? They didn't have this analysis. So Mosley, back in the very early 1900s, devised this method where by crashing electrons into a material and seeing what X-ray photons come out, you can actually very directly measure the frequency of the K-alpha line, or the square root of the frequency of the K-alpha line tells you how many protons are in the nucleus. So you can specifically measure, like for aluminum or for copper, how many positive charges, or protons in the nucleus, not electrons, how many protons are in the nucleus by the K-alpha line, the X-ray given off when the electron falls in from the second orbital into the first. So it was a way of basically verifying the order of the periodic table. And now we know very specifically the periodic table is in the order it's in because of the number of protons in an object. Hydrogen is first because it has a single proton. Helium is second because it has 2 protons. Keep going on. Oxygen has 8 protons. Neon has 10 protons. And you can keep on going through the list. Uranium has 92 protons, and so on. The order is specific, and you can test it using this method. Now, if you recall, when we looked at Bohr's model of the atom, the electron of some orbit, in this case n is 1, 2, 3, and 4, is equal to negative, because it's a bound orbit, z squared, where z was the number of protons in the nucleus. So here we had z. So for hydrogen it was 1, helium 2, helium 3, boron 4, and so on. Or lithium 3, sorry, beryllium, boron, carbon, nitrogen, oxygen, and so on. Over n squared, where n could be 1, 2, 3, 4, and so on, times some ground energy, some base energy, when n is equal to 1. The stronger the number of protons, the more the attraction is felt between the electrons as they fall down. Now, there's one problem though. There are only 2 intershell electrons. We'll learn about that in just a bit. Only 2 intershell electrons. So if you get rid of one of them, the outer electron here feels an attractive force, but it doesn't feel an attractive force of z. There's still an electron here shielding z. So really the force, it's as if the proton has a charge of z minus 1, where z is the number of protons. So if there are 10 protons pulling on this electron, there's 1 electron pushing on it. So the equivalent is the same as if 9 protons were pulling on the nucleus. So in reality, for this Mosley plot, it's z minus 1, not z, as we had derived before. And then the change in energy of these transitions is equal to Planck's constant times the frequency of the light. And then you can plot, again, in the Mosley plot, pop it up here once more, the square root of the frequency. So if you plug in frequency here, Planck's constant frequency here, you can see how it's related inversely to, or directly to, the, plug in frequency over here. We can see how it's equal to z minus 1 squared. So it's proportional to the square of z, or the square root of the frequency is proportional to z, as shown in this Mosley plot. And incredibly useful for the periodic table. X-rays also, we'll learn, are very useful in talking about crystals, and we'll talk about that in a bit. Finally, your book looks at a few other uses for X-rays. It does talk about using X-rays to measure properties of solids, specifically crystals. So in the little overhead view window here, you can see that in a crystal, the atoms line up as little slices, as little planes. So when X-rays come in, they can reflect off of those planes. And if X-rays reflect off of planes of different depths, when they come back together, they can experience constructive and destructive interference, just like light going through slits of different separation, like in a diffraction grating. So diffraction, X-ray diffraction and crystallography allows scientists to probe the inner workings of a crystal to look at the interior order of how the atoms are arranged in a crystal. And different crystals have many, many different ways of packing in atoms. And we can probe that using X-rays. Again, because X-rays are short wavelengths that are about the same distance as the spacing between atoms. Regular light can't do this. If you shine light through a crystal, the light will be basically move right through the crystal. You won't get this type of interference because visible light waves have a much, much larger wavelength than the spacing between crystals or adjacent atoms in a crystal. Finally, most of you are familiar with the X-ray, right? The image, the diagnostic tool used in medicine to basically see through your body. Before the medical X-ray, the only way you saw your bones was either through horrific injury, or that's basically it, horrific injury. Now, with modern technology, we can actually shine X-rays through a person, and in the soft tissues, the X-rays have very little trouble passing through. You can expose the film or the digital camera on the other side easily, whereas the bones, the denser bones, are more likely to absorb X-rays, so you can see the contrast between bones, harder, denser bones, and soft tissue more easily, giving a medical X-ray. When Röntgen, the discoverer of X-rays, first took an X-ray of someone, he actually took an image of his wife's hand, and you can see the bones in her hand, and she was wearing a big ring at the time. And when she saw the image, she reportedly said, "Oh my goodness, I've seen my own death." Fortunately for us, we have a lot of wonderful medical uses for X-rays. And not just bones and soft tissue. If you have soft tissue of different densities, like cancers, you can pick up sometimes those changes using an X-ray. Now, X-rays are ionizing radiation. So when they're absorbed by the body, usually that means they're absorbed by an atom or a molecule that kicks off a high energy electron. That electron goes barreling through the body, crashing into different molecules, potentially breaking them up. So if you've ever wondered why, if you get a medical X-ray or you get a dental X-ray, why the operator runs behind a lead-lined wall when they take the picture, it's for you a dental X-ray taken once a year, not a big deal. For them taking potentially dozens or hundreds of pictures every day, that can build up and damage tissue over time. So that's why you see them run out. Now, with modern technology, we can actually take a CT scan. A CT scan is a computer tomography. It's a way of combining several X-ray slices together into a 3D image of the human skeleton or the human body. So you can very accurately and very precisely locate injury. For example, if you have an artificial hip installed, is it sitting well in the socket? You can take a CT scan of that and really get good detail as to the three-dimensional structure in a body. Now again, it's ionizing radiation. CT scans are not something you should be doing often, but they are fairly quick to do compared to MRIs, which are far more involved and detailed, and a wonderful way of seeing bones and other dense material in the human body. Sometimes you get a dye injected, and then that dye will go through your blood system, and that can also help determine the dye will absorb X-rays, and it can help determine structure in the soft tissues, not just in the hard bony tissues. So X-rays are incredibly useful things, medically, scientifically, but they are dangerous. It is ionizing radiation. X-rays can cause damage to soft tissues or tissues over time, so it's not something you want to play around with. A microwave oven, perfectly safe, non-ionizing radiation. X-rays are not safe light. It's not a safe range of electromagnetic radiation. So we went through X-rays, and we'll be talking more about atoms in the next lecture.